It's a pleasure to have Brian Label here. He's the Emeritus Professor of Physics at UCSD. He's my academic uncle. Even though we were both graduate students at the same time, I think my advisor was a graduate student at the same time in the same group as he was. It's the Matthias group, and he's got the chair. It's the successor chair to Baron Matthias. Many of you don't know Baron Matthias. He's essentially a magician. He's responsible for most of the interesting superconductors and magnetic materials that were discovered in the 60s and 70s. And his group is largely responsible for all the developments in high-temperature superconductors that took place later in the 80s. Brian, in fact, was the organizer and chair of the famous Woodstock of Physics, which came just after the discovery of high-TC. He's done lots of stuff on his own as well. He has awards, the David Adler Lectureship, the James McGrory Prize. He's a member of the National Academy of Sciences. And you will tell about what he's been doing more recently.
Sure. So I know very little about terms that involve the word Woodstock. I'm familiar with quite a lot of what Brian's group has been involved with in the last few years. A lot of the most interesting quantum materials, as I go back and try to bring myself up to date on new things I might want to study, I'll find that Brian's name is attached to the discovery of the variant that I'm looking at, or to the exploration of it. One of our speakers last semester, was it? Joe Chakelsky or the semester before, had made the point that we don't have enough people doing synthesis in the US now, and a lot of that has moved to other countries. And Brian's group is one of the bright lights that we do still have in that. In particular, this family of materials built around this chemistry, uranium, ruthenium, silicon, has been very popular recently. It seems to realize a new state of matter that may not be found anywhere else. And it seems like most of the people who are doing the most interesting research get their samples either from Brian or from his students. Now, that's my angle, but when I moved into my office at NYU and was going over the books that used to belong to Peter Levy, I found a PhD thesis that dates back to 1969, which might have a tie into the Woodstock of sorts, which is apparently Peter was collaborating with Brian as far back as that time. So I'm very much looking forward to it.
Thank you. Well, I thank Paul and Andrew for inviting me, and I should have brought my historical talk about the Woodstock, but I actually do have one. Maybe I'll stand up here just for convenience. So anyway, I want to talk about the emergence of novel electronic phases due to competing interactions in correlated electron materials as a general topic. But I want to refer to this interesting case of uranium ruthenium-2 silicon-2, which exhibits a type of order that we can't identify at this point. And so let me just say a little bit about it. Anyway, there's been an enormous amount of interest in this compound during the past 3 decades, and there have been more than 1,000 papers written about this poor compound. And there's a delicate interplay between competing interactions that lead to a variety of correlated electron phases and phenomena. And so, for example, there's this hidden order phase that I mentioned. Order parameter has not yet been identified. But you also find unconventional superconductivity, antiferromagnetism, ferromagnetism, heavy fermion behavior. This is a heavy fermion compound. Quantum criticality, a non-Fermi liquid behavior, and some novel quantum phases in high fields that I'll tell you about. And these interactions, or these phenomena, can be accessed by tuning these interactions through chemical substitution, composition X, pressure, and magnetic field. So you find some very complex temperature versus composition pressure and magnetic field phase diagrams containing these phases that I just mentioned. There's been a quest to identify the hidden order of the order parameter of the hidden order phase, which has driven a lot of the interest in this material. But we've been mostly interested in it because it's a platform for studies of quantum phase transitions and criticality that can be tuned by varying these control parameters, composition pressure and magnetic field. So for example, if you apply a high magnetic field, you can suppress the hidden order, even though we don't know what it is, and find the emergence of quantum phases at high fields, as I mentioned. You can substitute rhenium for ruthenium, suppress the hidden order, and find itinerant ferromagnetism, an unusual type of non-Fermi liquid behavior. I'll briefly mention that. And then substitution of iron or osmium for ruthenium produces a transition from hidden order to large moment antiferromagnetism with a two-fold enhancement of this phase boundary, which I'll elucidate in a while. And there are two recent reviews by Maidash and Openair, which are very good, and if you want to avoid reading these 1,000 papers, you can learn a lot about this material in these two review articles. Okay, so in this talk I want to make a few remarks about correlated f-electron materials and quantum criticality, just for some background, and then talk about this uranium-ruthenium-2 silicon-2 problem with emphasis on experiment. Talk a little bit about the characteristics of the hidden order phase and efforts to identify its order parameter. It exhibits unconventional superconductivity, is regarded as a candidate for topological superconductivity. And then I want to concentrate on the transition metal substitutions for ruthenium in this compound. Again, you get these complex phase diagrams and quantum criticality. But in particular, if you substitute iron and osmium, it appears to open up an avenue which may allow one to hopefully identify the order parameter for this hidden order phase. Okay, so let me say a little bit about correlated f-electron materials and quantum criticality. So the correlated electron materials are mostly based upon transition metals, 3D transition metals, 4F lanthanide ions and 5F actinide ions. We're going to be concentrating on uranium, which is right here. And in these materials, these F states are admixed with the conduction electron states, which gives you the strong correlations and the interesting physics. And so since this is a heavy fermion compound, let me say a little bit about that. These are metallic f-electron compounds with enormous electronic specific heat coefficients, gamma, as high as several joules per mole Kelvin squared. And just to remind you, in a conventional metal, gamma is a few millijoules per mole Kelvin squared. So this is, can be 1,000 times as large. And from this, you can infer an effective mass between, say, 100 and 1,000 times the free electron mass. Again, this is generated by these lanthanide or actinide ions with partially filled f-electron shells and unstable valence. And these are the lanthanide species where you find this type of behavior. And then you can also find it for uranium and plutonium. We don't work on plutonium, but we do work on uranium. And this gives rise to hybridization of these localized F and conduction electron states. And without going into the details, this can produce a Kondo effect or valence fluctuation type physics, which is characterized by strong electron correlations and produces a non-magnetic ground state in these materials. And so what you find that there's a characteristic temperature, we'll just call it T star. It could be a Kondo temperature, it could be a valence fluctuation temperature, but it acts more or less like an effective Fermi temperature. And so at temperatures much larger than this, you find local moment behavior. The magnetic susceptibility behaves like a Curie-Weiss law with a moment close to the free ion value. And then the Curie-Weiss temperature, T star, is not a measure of where magnetic order occurs. It's a measure of the interactions that produce this highly correlated ground state. And then at low temperatures, as I said, you get a non-magnetic ground state. It's a heavy Fermi liquid. And so the susceptibility will approach a constant value proportional to the effective mass and proportional to 1 over the effective Fermi temperature. Similarly, the electronic specific heat coefficient, gamma, will become constant, proportional to m star and 1 over t star. Again, this can be as large as several joules per mole Kelvin squared. And this ratio, called the Wilson-Sommerfeld ratio, is of the order of 1, and it tells you that you're dealing with heavy itinerant electrons. You also get a narrow resonance in the density of states near the Fermi level. In the Kondo model, it's called the Kondo resonance or the Abrikosov-Soule resonance. And this heavy Fermi liquid is unstable to some very interesting types of unconventional superconductivity, which I won't be saying much about, and then magnetic order via the RKKY interaction. Yeah.
If you do what? It's unstable.
Oh,
by
well,
adding degrees?
well, you just find that some of them are superconducting. And also you can generate, I'll show you an example shortly where you actually do something and get superconductivity, unconventional superconductivity. That's a good question. Okay, so let me just show you a few examples. This is resistivity versus temperature for cerium aluminum 3, uranium beryllium 13, cerium copper 2, silicon 2, and uranium 2, zinc 17. And so you see as you lower the temperature, you get this dramatic increase of resistivity that's reminiscent of a Kondo effect. And then it reaches a maximum and drops precipitously as you go into this highly correlated ground state, where these ions, which at high temperatures were carrying local moments, now become non-magnetic and thereby become equivalent, and that then causes the resistivity to drop to a low value. And then you can see for this one, rho is proportional to t squared, so that you see the Fermi liquid type behavior. And then for magnetic susceptibility, for these two examples, at high temperatures, it resembles a Curie-Weiss law. The moment's close to the effective moment that you would predict from Hund's rules. And then you get a negative Curie-Weiss temperature, which is a measure of this interaction temperature T star. And then the susceptibility becomes finite, indicating that you have a non-magnetic ground state. And then the most dramatic thing is C over T, or the electronic specific heat coefficient, plotted here versus T squared. And you see that it rises dramatically up to a value of about 1 joule per mole Kelvin squared at low temperatures, and corresponding to a very large effective mass. And then this also becomes superconducting. And so here's specific heat versus temperature. You see this jump. And this jump is of the order of gamma times Tc, which is close to what the microscopic theory of superconductivity would lead you to suspect. And this tells you that the heavy electrons responsible for the large gamma are also involved in the superconductivity. And here's one way in which you can kind of visualize how you can get this heavy fermion state. So this is based upon an idea due to Neville Mott back in 1974. So this is energy versus K, so you have a broad, say, SP band right here, and then an F level or narrow F band crossing, intersecting this band right here. And so the bands will hybridize and repel each other, and so you're left with a small gap. And then, depending upon where the Fermi level is, you can get a heavy fermion hole-like metal or electron-like metal, say if it lies up here. And then you can also get a semiconductor, and these are referred to, at least in the old days, as hybridization gap semiconductors. Nowadays, people call them Kondo insulators. So an example is samarium boron 6, which has also been of interest recently because it's a possible correlated topological insulator. Okay, is this going to work? Yeah, here we go. Okay, so I want to say a little bit about, and a very little about quantum phase transitions. So these can occur at some value of a non-thermal control parameter, like composition pressure or magnetic field, where a spin or charge ordered phase is suppressed to 0 Kelvin. And so if you have a second order quantum phase transition, then this becomes a quantum critical point. And then you can have quantum fluctuations of the order parameter near the quantum critical point, which produces a breakdown of a Landau Fermi liquid theory in the vicinity of the quantum critical point. And you get a phenomena or set of properties that are referred to as non-Fermi liquid behavior, which are characterized by weak power law and logarithmic divergences in temperature. So if you look over here, you see how a Fermi liquid behaves. Resistivity goes as T squared, and then specific heat and susceptibility approach constant values. And the imaginary part of the magnetic susceptibility, which you would measure, say, for neutron scattering, scales like energy over the real energy over the Fermi energy, or omega over frequency over the Fermi temperature. It's the way it's usually expressed. But in a non-Fermi liquid, then this exponent can range between 0.5 and 1.5. It's usually close to 1. The specific heat over temperature usually diverges as log T, or a weak power law that's close to that. You get various non-Curie Weiss forms of susceptibility, and then in some cases you can get this omega over T scaling, where the Fermi temperature just gets lower and lower and gets renormalized through these quantum fluctuations. Okay, and so I've schematically indicated here some scenarios. Let me just say that you also find the emergence of superconductivity and other quantum phases near the quantum critical point. And so the way I kind of think about it is that these phases will envelop and protect the quantum critical point by removing the degeneracy, which I presume would be associated with these order parameter fluctuations near zero temperature. And so what you actually find in many, many cases is unconventional superconductivity, or for example in cerium indium-3 and many high TC superconductors, and exotic types of magnetic order as found, for example, in manganese silicide under pressure. So this is just schematic. So here would be the classic situation. You suppress some second order phase transition to zero. You find a non-Fermi liquid behavior in this region. It crosses over to a Fermi liquid right here. Sometimes, for reasons that I don't think anyone understands, you find that the non-Fermi liquid behavior extends out to high values of this control parameter without any readily identifiable quantum critical point. And then, interestingly, in this scenario, you sometimes see a dome of superconductivity that envelops the quantum critical point. And you can see it for this case as well. But it's even richer than that. Sometimes the superconductivity is only in the ordered phase, and then sometimes it abuts up against the ordered phase and appears like this. In this range, you actually see coexistence, and in this range, there is no coexistence. So these scenarios are very rich and worth investigating by themselves just to find out more about these various phenomena. So anyway, I'll just show you a couple of examples. This is cerium plating. Yeah, sorry.
If you could go back.
Sure. Mm-hmm.
What precisely is the order you're talking
well,
about?
it's usually magnetic order, but in principle it can be anything. I mean, we know of systems that exhibit charge density waves where you get, and Paul, you must have worked on some of those, where you find that you can suppress the charge density wave and get a dome of superconductivity. So I guess I'm referring to magnetic order here, but it's more general than that.
But you didn't show us any of that.
I didn't show anything like that. Although in the case of uranium ruthenium-2 silicon-2, we don't even know what the order is. Okay?
That's the hidden order. That's the where the so-called hidden order resides.
In that material.
In that.
Yeah, in these materials, we presume to know what the order is. Okay. So I'll give you a specific example. Here's cerium platinum-2 silicon-2, so it's an antiferromagnet, and Julian and Lanzarich and co-workers applied pressure and suppressed the nail temperature, and it looks like it's going to extrapolate to a quantum critical point at about 28 kilobars. And what they found before they ever get there, there's a dome of superconductivity that develops that's shown in more detail in the inset. And then furthermore, if you look at the resistivity, this is plotted versus t to the 1.2 power, then this varies as t to the 1.2 between Tc, which is about 0.4 Kelvin, all the way up to 40 Kelvin, and that's a non-Fermi liquid-like behavior. It's not T squared.
Along what path would that be in the main graph?
That would be right here. So I'd be coming down at 28 kilobars, right in the interesting region where
Fixed pressure.
you get the superconductivity. Yeah.
At fixed pressure.
Yeah. Okay, and so anyway, this suggests that the antiferromagnetic spin fluctuations that are responsible for this non-Fermi liquid behavior are also involved in the superconducting electron pairing in this and similar materials. Okay, and so this happens in all kinds of materials. I'm just showing you another example. These are some iron-based superconductors, occurs in the cuprates and many other heavy fermion materials. And this just shows you different scenarios where you're, in this case, changing the fluorine concentration, in this case, the potassium concentration, in this case, cobalt. But you're always suppressing antiferromagnetism or spin density wave transitions, and then producing superconductivity that occurs in the vicinity of the quantum critical point, and in some cases it overlaps and even coexists. Okay? So anyway, that's just some background. So now I want to go back to uranium, ruthenium 2, silicon 2. Excuse me. You'll see some similarities. So here is some early work back in 1986. There were 3 groups that reported on this at intervals of 1 month in the literature. And the group that discovered it was Schlabritz and co-workers in Cologne. And then John Maidosh's group worked on it, and our group worked on it. And we had papers published at about the same time. But this is from John Maidosh's group, and this is resistivity versus temperature. And these are single crystals, so you again see the kind of behavior that I showed you, kind of like resistivity, and then it turns over and drops precipitously. But in this case, you find some kind of order that occurs at 17.5 Kelvin that looks very much like a spin or charge density wave transition. And then at lower temperatures, it becomes superconducting, as indicated here. And then if you look at the C-axis susceptibility, it has Curie-Weiss behavior at high temperatures, and then rolls over, and then has a drop due to this order, whatever it is. And this early work generated some some neutron diffraction experiments by Colin Broholm and co-workers. And basically what they found was that this was a C-axis antiferromagnet with this structure right here, but it had a magnetic moment of only a few hundredths of a Bohr magneton. Okay? Okay, and this is from our own work. Here I've plotted C over T versus T squared, and you see this pronounced anomaly at 17.5 Kelvin, and it's a BCS type mean field transition, it looks like. Again, we thought this was a spin or charge density wave, and you can take this exponential part and infer an energy gap of about 130 Kelvin from it. And also you'll notice that if I extrapolate C over T versus T squared from high temperatures, that will give me a gamma value that I would expect if it didn't exhibit this magnetic order. Hidden order. And then, of course, the actual gamma before it becomes superconducting is this value right here. So if you take this ratio, then this suggests that about 40% of the Fermi surface is removed by what we thought was a spin or charge density wave. Okay? And then at lower temperatures, the rest of the Fermi surface is removed by the superconductivity. In fact, Paul, I think you worked on a similar compound and inferred similar behavior. Do you remember that? Yeah, I think so. And then the effective mass is about 25 times the electron mass. Now it turns out that there's a large amount of entropy removed here of about 0.2 log 2, and it's too large for such a small magnetic moment, and this is what gave rise to the terminology hidden order, and as I mentioned earlier, the order parameter of this phase has not yet been identified after 3 decades of research. Okay, so there were some pressure experiments made by Mitska and co-workers from neutron scattering, neutron diffraction basically. And so this is a plot of magnetic moment versus temperature. And this is at 0 pressure. This is at 28 or 2.8 gigapascals or 28 kilobars. And then as you increase the pressure, you find that the magnetic moment increases, but then it jumps up abruptly at about 15 kilobars to a large value of about 0.4 more magnetons per uranium ion. So it's low over here, although it does increase, and then it jumps up to 0.4 more magnetons. If you do NMR, such as done by Matsuda and co-workers, you find that at 0 pressure, you only see a feature due to ferromagnetism. There's nothing, well, a very small feature associated with antiferromagnetism, and it stays basically paramagnetic until you get to a pressure of, let's see, I guess this is about 8 kilobars, and then you start to see these antiferromagnetic wings increasing and the paramagnetic signal decreasing, and then at the highest pressures you only see the antiferromagnetism. So this was inferred, from this was inferred a situation where you get phase separation, that the neutrons basically measured the average moment, and that this looked at the moments associated with the 2 phases individually. And so basically it was concluded that the hidden order phase doesn't carry much magnetism, and it's really an antiferromagnetic phase comes in at higher pressures. Okay, and here's the proof of that. So this is magnetic moment versus temperature, again measured under pressure. And so you see that the moment, it's similar to what I just showed you. The moment here starts to increase when you get to about, let's see, this is, sorry. Yeah, 7.6 kilobars. I'm trying to convert here from one to the other. And then it starts to increase. And then it's very sharp, indicative of a first order transition. And it goes up to 0.5 more magnetons per uranium. And then you can deduce this temperature versus pressure phase diagram. And so here you see that the hidden order transition follows this line, and then there's a kink when you go into the antiferromagnetic phase. And then this is a line of first order transitions right here. The superconductivity lies in this region right here, and so it looks like that it coexists with the hidden order, but does not coexist with the antiferromagnetic order. Okay, so again, you see, a quantum phase transition right here, and you see a magnetic phase, and then a phase whose order parameter you don't even know, and then superconductivity occurring in this region right here. Okay, and these are other measurements made by other people earlier on, and so we weren't the first people to do this by any means, but this experiment was done using helium as the pressure transmitting medium, so I think this is a more reliable phase diagram. So the other people that worked on this earlier are listed here. I don't want to give you the impression that we were the first to do this. Okay, so a little bit about the characteristics of the hidden order phase. So it certainly has an energy gap of about 100 Kelvin. It has itinerant character, which I think is consistent with this partial gapping scenario that we proposed. It has to have local character, so you have hybridization of localized 5F and conduction electron states. And as you've seen, the small moment antiferromagnetic phase resides within the hidden order phase and is presumably responsible for this small moment. And I think the general view is that this is an extrinsic effect where you have internal strain which frequentia, small concentrations of the antiferromagnetic phase. Now, to be fair, there are some people who believe it's intrinsic, and evidence for that is that samples of widely varying quality, at least measured by neutron diffraction, always give you a moment of a few hundredths of a Bohr magneton, and the antiferromagnetism onset is at T0. Okay? But I think most people think it's extrinsic. So the energy gap has been observed in many experiments. All of these old experiments indicated here. Also in infrared spectra, tunneling spectra, spin excitation spectra, STM studies. And so the energy gap certainly is one feature of this phenomenon that is solid. Okay, now this has led to at least 30 theoretical proposals, models, which are all, this is a partial list, so many of them are indicated here. And so this is an active field where people are trying to propose what it could be and then trying to do measurements to, establish what it actually is. And so Andrew is one of these people trying to find out what the ground state is so that one can see what kind of theory that you can even start out with. Okay, now a few features about the hidden order phase. So these are some Shubnikos-de Haas measurements on uranium, ruthenium-2, silicon-2 done under pressure. So this is in the hidden order phase right here. So these are the amplitude versus frequency spectra. And this is in the antiferromagnetic phase, and you can see that they're not too different. And then when you look at the actual frequencies versus pressure, you see that they don't change much when you go from the hidden order phase at lower pressure into the antiferromagnetic phase at higher pressure. And then also the effective masses go through here rather smoothly. So this is, suggests that these two phases are rather similar, and some people suggest that one actually grows at the expense of the other as you go through this transition. Okay? Neutron scattering measurements have been made. This is energy versus in a certain k direction. And here what you see is that there's two distinct gap modes at the hidden order transition. There's, or come in at the transition, there's a commensurate mode that has a 2 millivolt gap. This is right here. So this is 100. And then there's an incommensurate mode that comes in at 4.5 millivolts right here. So above T0, the excitation spectrum is dominated by fast itinerant-like spin fluctuations up to at least 10 millielectron volts emanating from these incommensurate wave vectors. And this is believed to be associated with heavy quasi-particle excitations that form below the coherence temperature. That's the temperature where the resistivity rolls over and you form this heavy fermion ground state. And so these excitations are involved in the formation of the heavy fermion and hidden order states. And then below T0 you get this gapping that gaps out these strong spin fluctuations and could then provide a mechanism for removing the entropy at the transition. And so, generally one has a picture where this hidden order transition seems to involve the rearrangement of electrons at the Fermi surface, which shows you that this has itinerant character in addition to this localized character. Okay, I'll just tell you a few other things. As I mentioned, there's some X-ray edge absorption measurements that have been made by Corwin Booth, where Corwin, I think, concludes this is a 5F3 configuration for uranium, and Andrew, I think, is proposing something closer to 5F2, although it may not be possible to say that it's purely one or the other, but it's very important for these various models that people are pursuing. There's also a report of electron nematicity. So when you look at very small specimens, there's symmetry breaking in the basal plane, this is a tetragonal crystal. So there appears to be electron nematicity, although I think this is somewhat controversial at this point. And then there's giant Ising anisotropy of the conduction electrons, which you can deduce from magnetic field orientation dependent measurements of quantum oscillations and the upper critical field, which is Pauli limited. And so this suggests that you have quasi-particles that are, I can show you on the next slide, whose G factor is highly anisotropic and located in the C direction, or is finite in the C direction. So that's these curves right here. This is the polar angle. And then you see if this was a ordinary conduction electrons, you would expect to get this behavior right here, which would be isotropic for the G factor. So there's lots of things that are known, but nobody yet has identified what the order parameter is. Let me just say a little bit about the superconductivity. This is based upon thermal conductivity measurements in a field and as a function of temperature. So this has line nodes on the Brillouin zone boundary on the spherical light hole-like Fermi surface. So this is a spherical light hole-like Fermi surface. This is a line of nodes. And then you have point nodes on both the spherical light hole-like Fermi surfaces and elliptical heavy electron-like Fermi surfaces along the C-axis right here. So these are the point nodes. So these are the Fermi surface sheets. And then these are supposed to represent the energy gap, okay? And you have spin singlet pairing and basically superconductivity with two distinct gaps having different nodal topology. And as I said before, this has been suggested to be a candidate for a topological superconductor. Okay, so now let me come to these transition metal substitutions that we've been involved in. See how time is going here. If I can show you at least a little bit of this. So basically, we've looked at substituting for ruthenium, manganese, technetium, and rhenium, which are in this column. So this dopes the system with holes. And what this does is it suppresses hidden order and gives you the emergence of itinerant ferromagnetism. And this we discovered back in 1989, but have studied in more detail since then. For rhodium, it's known from work in Japan that you can then dope the system with electrons, and this suppresses hidden order, and you get the emergence of antiferromagnetism. And then more recently, we found that substituting iron and osmium, which is an isoelectronic substitution, produces a transition from the hidden order to the large moment antiferromagnetism that's very similar to what happens under pressure, okay? And so let me just show you the rhodium and the rhenium cases. Again, I'm not going to go into any detail, but for rhodium, you see hidden order here, antiferromagnetism, and then this gap where nothing particularly interesting occurs. Then you get complex antiferromagnetism, another gap, and then high temperature antiferromagnetism. For rhenium substitutions, you suppress hidden order, and then you get this weak ferromagnetic ordering, and then in this region some unconventional type non-Fermi liquid type behavior that I'm not going to go into. So anyway, it just shows you get some very interesting and strange things, and it's even going to become stranger in a while. So let's look at these iron and osmium substitutions. And then let me just say that I think this is important because what we found, as I mentioned, is that substitution of iron for ruthenium is analogous to the application of pressure in pure uranium ruthenium to silicon 2 in driving this hidden order large moment antiferromagnetic phase transition. And so you have similar phase diagrams for Tc versus X for this substitution as you do for Tc versus pressure for the pure compound. And so we found that you can think about this as if you have a chemical pressure that's associated with the reduction in the unit cell volume. And so as you increase X here, one way of thinking about it is that you're increasing the chemical pressure. Okay? So the iron concentration then can act as a control parameter that again allows you to access the hidden order phase at ambient pressure. And why I think this is important is that you can now do experiments using techniques that are difficult to employ under pressure, like ARPES and STM. Inelastic neutron scattering you can do, but not to too high pressures. And then some high magnetic field studies that I'll show you in a moment. So you can do things where you can access this phase that otherwise you can only reach under pressure by doing these substitutional type experiments. And we're pursuing this with a number of collaborators, including Andrew. Okay, so here then is the TC versus X phase diagram. So again, we're substituting, in this case, iron for ruthenium. It's isoelectronic. And so in the early exploratory experiments with polycrystals, this is the only way you can work fast enough to do these exploratory things, is that we found that temperature versus iron composition gives you a phase diagram that looks like this. And these are little spurious features due to the fact that we're working with polycrystals, so just disregard them. There's a kink in this phase boundary that occurs at a chemical pressure very close to the kink that occurs under pressure in the pure compound. So we think this is where the transition from hidden order to large moment antiferromagnetism occurs. And then you see that this goes over a peak very much like the phase diagram does at higher pressures from other work in the past on the pure compound. Okay? So we think then that this is the transition where you go from hidden order to large moment antiferromagnetism. So we've now spent many years growing single crystals, and so I won't bother you with the details, but there's such a single crystal. And what we found that if you now do neutron diffraction, so here's magnetic moment versus temperature at various iron concentrations, increasing in this direction, then you start out with a low moment. The moment increases up to, in this case, about 8 Bohr magnetons, and then thereafter it decreases slowly. So we believe that this is the hidden order region right in here that you can now transform into large moment antiferromagnetism as a function of iron concentration. And so, again, I'll go through this very quickly. So anyway, you make a lot of single crystals, you make a lot of measurements, and so these are various resistivity measurements at various iron concentrations. You can, and this is the derivative of these resistivity curves, you can easily pick out the temperatures where you get the hidden order and large moment antiferromagnetic transitions. And this is for magnetic susceptibility, basically the same thing. This is the derivative of susceptibility times temperature, temperature with respect to temperature, versus temperature. So this kind of gives you what the specific heat should look like. And then this is actually the specific heat. So it's very sharp and large in the hidden order phase and smaller and more spread out in the antiferromagnetic phase. So, and then you can do thermal expansion measurements, which is where quantum design came in with some equipment that they developed. And so this is a thermal expansion in the AB plane. This is along the C-axis. And again, you see a lot of features. You can then deduce from this the volume thermal expansion shown right here. So I'm not going to go into the details, but for some of these transitions at 0.8 Kelvin, 0.08 iron concentration, X, and 0.1, you actually see two transitions that are indicative of going from the paramagnetic phase to the hidden order phase and then into the antiferromagnetic phase. And so that's shown here. Again, here's the features here. I won't belabor you with the details. But from all of this, you can then construct a phase diagram of temperature versus iron concentration. So here's the kind of a overall view, and this is more detailed in the neighborhood of the transition point, right up here. So again, you see that this phase boundary is not vertical, and we're trying to measure in more detail what it looks like in this region right here. Sorry, I'm losing my voice here. So anyway, that looks very much like the temperature versus pressure phase diagram for pure uranium ruthenium-2 silicon-2 that I showed you earlier. Okay, so anyway, you can look at these features. So this is resistivity, specific heat, and volume thermal expansion. And they have parts that can be analyzed in terms of an energy gap. And these are the energy gaps that we deduce at various concentrations, X. So this is energy gap versus X. And you can see that as you go through the transition, energy gap decreases, and then it jumps up and decreases. So there's an energy gap in both the hidden order and the large moment antiferromagnetic phase, and you can see that it behaves similarly as deduced from these three different measurements. And this shows the pressure dependence of the hidden order and the large moment and the Néel temperatures. So this is the hidden order phase right here. And you can deduce these from the Ehrenfest relation. So this is for thermal expansion, these triangles, AB plane, C-axis, and then you can deduce the volume thermal expansion, the volume effect. And then what's shown here from the red points is the actual measurements of these transition temperatures as a function of pressure, okay? And so you can see that you can very clearly define the transition from the hidden order phase into the large moment antiferromagnetic phase. All right, and so we wondered about this equivalence between pressure and iron concentration, and so we thought, well, we can do some studies under pressure, and if the iron concentration was equivalent to adding a chemical pressure, then as we increase the iron concentration, the pressure at which the transition occurs should decrease as determined from the kink in this phase boundary. And so for the pure compound, here's the kink at 1.5 GPa or 15 kilobars. And then as we add iron, you can see that this kink shifts to lower and lower pressures, okay? And then eventually there is no kink when it becomes purely antiferromagnetic. And so from that you can deduce a three-dimensional phase diagram of temperature versus pressure versus iron composition, and then if you just extrapolate these points downwards into the XP plane, you can then define a region where you get hidden order and another region where you get large moment antiferromagnetism.
Is susceptibility?
Yeah. Mm-hmm. Beg pardon?
Was that susceptibility that you were plotting?
No, that, okay, let me go back. Okay, this is basically the temperature at which the hidden order phase occurs in this region right here. And then this is the large moment antiferromagnetism, and there's a kink in this phase boundary when you go from one to the other. So as we add more iron, we're presumably increasing the chemical pressure, and so this should occur at a lower applied pressure, which it does, and then eventually at zero pressure when it's purely in the antiferromagnetic phase. Okay? So this shows you that they're at least equivalent, as I've indicated here. Okay, so let me say a little bit about I'm going to come back to this point in a moment because it's not going to be as clear as it seemed. So let me just show you as a last example some, I mean, we've done a lot of measurements, done neutron scattering and some infrared absorption measurements with collaborators, but I just want to show you one last thing that I think is illustrates the richness of the physics in this system, and that is electrical resistivity measurements in very high magnetic fields up to 45 Tesla at the National High Magnetic Field Laboratory in Tallahassee. And so this is earlier work done on pure uranium ruthenium-2 silicon-2, and this is resistivity versus magnetic field. And so anyway, these are just various features that you can pick out in these resistivity curves, which are quite complex. And then you can deduce phase boundaries in high field that look as indicated here. And then from the overall study, what they found was this more complex situation right here. So this is the suppression of the hidden order phase, and then you see a cascade of other quantum phases that occur in this region right here. There's a metamagnetic transition right here, and then this is the maximum in the resistivity that marks the coherence temperature, and it appears to terminate at a quantum critical point right here, and then you get a line emanating from that point along here where you cross over from non-Fermi liquid behavior to Fermi liquid behavior. And so in this region you see the exponent of the resistivity. It's about 1.5 throughout these phases in here, so that's non-Fermi liquid-like, and then when you cross over into this region it jumps up and becomes Fermi liquid-like right here. So this is another figure. It's kind of a cartoon, but it shows more clearly what's believed to be happening. So again, superconductivity is down here, hidden order in here. You get itinerant electron behavior here. This is the peak in the resistivity. This is the crossover to the Fermi liquid behavior, metamagnetic transition, non-Fermi liquid behavior in here, and this cascade of quantum phases at high fields. Now, interestingly enough, I'm not going to show you this, but if you now substitute about 5% rhodium in here, you can remove all these other quantum phases and the hidden order and just produce one of them at this point right here. Okay. So what we've tried to do now is to look at this iron substituted system. And so these are various iron concentrations, and these are the resistivity curves that you get. And then, trust me, you can analyze these and find features like in the, well, don't trust me, trust my postdoc who did this. You can then find features and construct phase diagrams. This is what we've done so far. We need to do more. But you can construct phase diagrams as shown here. So these blue lines are always the suppression of the hidden order phase. This is the metamagnetic transition. These red ones are one of these quantum phases, and the purple one might be a new quantum phase that we found in this system. Okay? So as you increase the iron concentration, all of these are in the hidden order regime, and you see similar features. And then you cross over into the antiferromagnetic regime, and you lose those quantum phases. And so here, for example, you find that you suppress antiferromagnetism, and then hidden order grows out of it, and then you get the metamagnetic transition, but none of the other phases. So we're in the process of trying to study this in more detail, and so these are some false color plots showing some of these lines, and these colors represent the value of the resistivity. They make nice figures, but they're not so easy to understand. But you can also construct a three-dimensional phase diagram. So this is temperature, iron concentration, magnetic field, and so you see over here is hidden order being suppressed as you increase the field. Iron concentration is increasing this way, and then you see that you get large moment antiferromagnetism, and as you apply field in this range, you suppress that, and then hidden order grows out of it, and then you see the metamagnetic transition feature here, and then some other features due to the other quantum phases. And so this is just another view, showing you these quantum phases in here. So we don't understand this very well. We've got to do obviously more experiments, but this just shows you how rich all of these competing interactions are in giving you all these novel phases, and so it's going to be a challenge to develop a real understanding of what's going on here. Let's see. Okay, let me just skip that. So anyway, as I said, we've done inelastic neutron scattering and other types of measurements. I'm just going to skip through those in view of the time. And let me just make one last point. Now, so we worked on this iron substituted system, and it turns out when you substitute iron, it decreases the unit cell volume So we knew that osmium increases the unit cell volume, so we would have expected that things would go the other way and you would decrease the hidden order. And so what we found was shown here. So this is the iron phase diagram that I showed you. Again, ignore these points right here. This is on polycrystalline data. So this is increasing the iron concentration, reducing the unit cell volume. This is substituting osmium, increasing the unit cell volume, and you see that the same thing happens, and the phase transitions even go to higher temperatures when you do that. So now we find that basically iron and osmium do the same thing, and so either this interpretation in terms of chemical pressure is incorrect, or it is correct and something else is driving it in the case of osmium. And so things that come to mind are spin orbit coupling and you know, maybe some other effects that we haven't accounted for. So that's at this point a mystery. Okay, this is just some other things. So let me just finish. So I think uranium ruthenium-2 silicon-2 is one of the most interesting heavy fermion f-electron compounds. You have this delicate interplay between competing interactions that you can tune with these parameters and generate these complex phase diagrams. You have a wide variety of correlated electron phenomena. And I think there'll even be more that are found as we proceed. And the single crystals, I think, have been very important and may actually give us a route for doing experiments at atmospheric pressure, you know, like STM and ARPES, which are underway, that may give us information that you can't get under pressure in studying the pure compound. Okay, so I hope that's a lot of things. I hope it gives you some flavor for the richness of this field. It's even probably too rich, you know. It's very challenging, but it's certainly a lot of fun. So, thank you.
In the beginning, you mentioned unconventional superconductivity.
Yes.
It passed you by. What did you mean?
Okay, what I mean is superconductivity that has features that you don't see in BCS superconductors. So, for example, a lot of these, or many of these materials, break time reversal symmetry when they become superconducting. A lot of them.
Iron.
Pardon?
The one doped with iron.
Oh, yeah, this one does, for example. And then other ones like certain more filled Scuderdite materials we work on, they break time reversal symmetry. There's evidence for point nodes in the energy gap or line nodes. Certainly in this case, you saw nodal regions on the energy gap. So that's one.
So you mean non-S wave?
A non-S wave, and then I could even say that the pairing mechanism would be non-phonon. And so in a lot of them, you know, if you have nodes, then you have sign changes in the energy gap, so you can then have a repulsive magnetic or electronic interaction that then can be rendered attractive, which, you know, it occurs in the cuprates, it occurs in cerium, cobalt, indium-5, which I didn't talk about, and in some of the pnictides it's more complicated because then you have different Fermi surface sheets, and you can have sign changes between Fermi surface sheets and then pair between them. And so there's evidence for that as well. So I guess I meant a lot of things, but certainly not simple BCS. So anyway, in the soft materials, Paul, that you work on, there, you know, are similar things, and, you know, I could have included those in this whole picture as well.
Didn't you want to give us a clue as to what you think the hidden order phase is?
Oh, well, I think it's still, I mean, I think it's what I thought it was in 1986. It's some sort of a density wave. Okay, but nobody's been able to identify it as a spin density wave or a charge density wave.
You have to understand that the science paper from last year that claimed to solve it And all of the people who've put their feet down and put out very strong opinions are using Brian's samples or samples from the students. So that's...
Well, that could be good or bad. I hope it's good.
If you could record him making statements on this,
Yeah. But I mean, in the organics, you know, you see a lot of these relationships between spin density waves and superconductivity, you know, the things that you've studied.
Right.
So I think it's very general, you know. It doesn't have to be just magnetic phase transitions.
Any last questions before we go up to where there might be food? All right, then let's thank Brian Williams.
Okay, thank you.